Welcome to the Gardien Group podcast series. The Gardien Group, providing extraordinary solutions to today's exceptional problems.
Hello, and wherever you may be, Todd Coleman again from the Gardien Group with another in our series of podcasts. Today we're going to talk about test point assignment and electrical test. Joining me today again from Toronto, Canada is Rick Moran. Good afternoon, Rick.
Hi, Todd, and thank you for inviting me to talk along with you. I know it's very exciting for me to give information out to others. It's very important to understand how to electrically test a bare printed circuit board, as we're about to find out today. Today, let's get right into it, Todd. What is a test point?
What is a test point? Well, in electrical test terms on a PCB, on the surface on one side or both sides, there's going to be what we call landing pads. And from an artwork standpoint, that could be either an SMT point or a plated through hole point. And if you look at our graphic that we have here, our test points 1 and 2 are what we call SMT pads. And test point 4 is a plated through hole. Test point 3 is also an SMT pad. And when we test these, we have some algorithms that allow us to test all points or some points based on the different classes of the IPC specification, either class 1, 2, 3, and we call those test levels 1, 2, and 3. In a class 1 or test level A, that's the most relaxed test point requirement, where all we need is endpoints. So in this specific graphic here, test point 1 would be tested, test point 3 would be tested, and the caveat here, test point 4 may or may not be tested, and that all depends on solder mask or accessibility of the point. But in class 1, basically endpoints only. Class 2 or test level B, we still can use endpoints and take out the middle point. So in this case, we'd be doing 1 and 3 and possibly 4, depending on the solder mask clearance or via plug. Where it gets different is when we get into class 3 or test level C. That's where they require the midpoints to be tested. So in that scenario, we would be having to test point 1, test point 2, test point 3, and test point 4 again if test point 4 was available from one side or the other to be tested. So in a nutshell, that's basically what a test point is and what a midpoint and endpoint is based on the graphic there, Rick.
Yeah, Todd. So a midpoint, you imagine this. Imagine a T, a capital T. The bottom stem of the T, let's call it test point 1. And then halfway up the stem of the T, we'll call that test point 2. And on the top of the T in the cross, we'll call the left edge a 3 and the right edge a 4. And that basically gives us 4 test points. As you remember, a PCB is a connection device. So you're going to connect your ICs or semiconductors to it. And all this creates current flow, electricity flowing through that based on Ohm's law. So we need to make sure the current flows from all those test points in one net. So from 1 to 3, there has to be current flow. 1 to 2, there has to be current flow. 4 to 2, there has to be current flow. And 4 to 1, there has to be current flow. So all across that net, there has to be connectivity. Now, if we were to eliminate point number 2 because it's in the middle of the stem of the T, current could still flow through there because it's a pad attached to a trace. The pad attached to a trace the trace still allows current flow. The pad just connects to that trace. So if the pad is there, it conducts current flow. So 1 to 3 would still have current flow if we didn't have a test point on 2. The current could still flow from 1 through 2 and to 3 without a problem. Or vice versa, the current could flow from 1 through 2 to 4. But you don't need to test 2 because it's classified as a midpoint. Todd, is there a difference between a surface mount test point or a hole test point?
Well, yes, there is, Rick. Actually, an SMT pad, or what Rick mentioned is surface mount, would be a pad that is only on the outer layer of the board where the test point would be touching. Then there's a PTH, or plated through hole, which our graphic shows. A PTH via shows the inner traces down the barrel. So the SMT pad is on the surface on either side, and the barrel is going through the center. So we can test the barrel or the SMT. The barrel test checks the integrity of the net, as well as testing if the barrel is an endpoint. We'll be testing the endpoint of the net, just like our example of the T. The barrel can be just one of those endpoints. The problem that exists is sometimes they do via capping, or on the plated through hole, smaller holes, the vias get capped or via plugged, which causes an encapsulation of the barrel, so that a test pin or a probe cannot successfully test the barrel without burying into the solder mask, and that causes erroneous opens and such. But that's on the smaller PTH vias or interconnects. Larger plated through holes, which are usually ZIF connectors or connectors that other boards plug into. These are larger holes, and these can usually be probed either direct center or on the annular rings. With flying probers, it's recommended that you do go to the annular rings. Most softwares out there can generate the offset to the test points, because on flying probes, the probes are either needle points or very, very sharp, and they'll have a tendency that sometimes cannot get a good contact if you're trying to hit the center of the hole. That also works. The problem is this: when the solder mask gets encroached, sometimes even on a plated through hole for a connector, registration of solder mask may bleed up onto the shoulder or the annular ring, and so testing of the ring is desirable, because you can do some offsets on that with probers, which you can't do with a direct test point if you're using a fixture tester where they used a music wire or a chisel probe.
So Todd, you mentioned barrel tests there. There are a couple questions came in my mind when you were speaking about that. It was a very good explanation. What exactly would you be testing when you're doing a barrel testing? I'm guessing you're testing the plated through hole, but isn't that normally tested anyways?
Well, depending on the class, when we talked about test points and what is a test point and optimization and so forth, sometimes these plated through hole barrels can be considered an endpoint or a midpoint, excuse me, so that they may or may not be tested. But if they are tested, you want to test those at the termination of the net. In this case, when you look at the graphic, you have your interlayer traces that are going through the barrel. Ideally, on this, if you are testing this to make sure that it is going to be functional at even the functional test, you need to test actually both sides of the barrel to make sure that the interconnects are can be probed or can be measured from either side of the barrel. Another thing with that, if there is a void in the barrel, which we may touch on that a little bit here yet, above where the interlayer traces connect to the barrel inside the board, you could have a void there where it does not affect the actual net list or the electrical signature of the board, but that gap between where the solid connections are and the top of the board, which may not be a functional problem. When they do a test after they do assembly, they could probe that point and find an open in the barrel. Doesn't affect the actual board electrical signature, but it will fail the board and cause a return. That's another thing with barrels, with especially smaller barrels. We've talked about this in the past, but high resolution testing, or sometimes called 4-wire Kelvin, we use high resolution probing on both sides of the via usually to make sure that we have sufficient copper in the barrel. And very small changes in copper weight can make a wide range fluctuation on the resistance value, and we can sometimes, or many times, be able to isolate a potential problem in the plating process before the board goes out to a customer out in the field and turns into some type of defect. And these could be latent defects. It could be months or it could be a year before something fails, but we sometimes, with doing this type of test, you can find this problem before it gets out to the customer, Rick.
Yeah, you mentioned four-wire Kelvin testing and the plated through holes. I know, and I call it the olden days, Todd. I feel a little bit older now. We did have some escapes for electrically the board was good, but partially the plated through hole was not plated on the one end, and it wasn't there captured during the electrical test process because of the way the test points were assigned. But more and more these days, a lot of people are assigning test points to both sides of a barrel hole. In automotive, I know these guys they want fast speed. They want speed of printed circuit boards. So they're even building boards or trying to produce boards, designing boards at 77 gigahertz, 94 gigahertz. And I heard talk about even going up to 140 gigahertz. So for them, doing four-wire Kelvin on a complete net is also important. You need to have the low resistance value. We know that the more copper you have in a net, the higher the resistance value goes. And it's all about current flow, right? It's always about the same thing. And PCB board is a connection device. We can build all these fabrication plants around the world now, but they're not really useful without a PCB. PCB is a major part of the role of electronic component or electronic device. Sorry about that.
Well, when you talk about PCBs or printed circuit boards, and I'm a new guy to the industry, let's say, and I have a PCB, and the sales group says they want it tested, and I have this PCB. I mean, what can you possibly test on a PCB? What all can you test?
Well, we know a PCB has some sort of conductive material and some sort of surface finish on the outer layers. So we can only test anything on the outer layers at this time. Maybe in the future that will change, but we can only test components or accessible points on the outer layers. So any surface finish, conductive surface finish that's open in the solder resist or solder mask can be tested. So if you imagine a circuit board and you did a section on it, a cross section on it, across the entire length of the board, I'm pretty sure you would see some copper plating from the top of the component side to the solder side of the board, some copper traces on the inner layers, some surface mounts on the exterior layers. So whatever on the exterior layers and not covered in solder mask, in theory, could be a test point. So those test points, you could use any one of them, all of them, for testing, because it's open and mask, and you can put some sort of testing to probe on there, create a current flow, a sense point, and a reading point, so you can measure the current flow, resistance, and you would be able to test the entire board. So that is, I think, the most efficient way to test a printed circuit board these days, providing you have the real estate and spacing in order to get your contact device into the surface mount. And that's why I think, Todd, they have a special classification in IPC 9252 for this, do they not?
Well, in the 9252, they have 3 different types of algorithmic test point allowance, class 1, 2, 3, which I touched on a little bit out of order early on in the presentation. But for a class 1 board, you just need to test the endpoints of the net, and you can have a lot of midpoints. In Rick's graphic now, we have the red being the endpoints on each one of those little pyramid triangles, whatever you want to call them. And then the midpoints are in green. And one of the things to note on the right side, the barrel that we show where it's outlining the PTH via and the inner layer trace, you can see that we have possible test points on, or midpoints showing on top and bottom of the board. And why do you ask that, you say? Well, if you look in there, you see the inner layer trace highlighted. You see 2 of those. So if we were to put a test point on either side, one or the other, you can see that the current will flow down the barrel and go out to both inner layer traces. So they may terminate at one of the other endpoints, but testing the top and the bottom of the board for the electrical signature in class 1 or class 2 is not necessary. So that's why they are identified as midpoints. Now in class 3, you would have to have a test point on either the top or the bottom of that barrel, along with the endpoints that those interlayer traces go to. And in some cases, when you get into higher reliability product, you actually need to enhance your testing as well when you get into hybrid aerospace and such like that. So, Rick, when we talked about the 9252 and current level of that specification is B, but in Class C, like I said, you have to do both the midpoint test points and also the endpoint test points. And are we allowed, there's also, when we start talking about military and aerospace, high reliability medical, and they used to call it in 6012, they used to call it the 3A aerospace exception, where we had to do some extra things, which we still do. Now they call it the 9012 DS or the 9252 DS, which deals with that high reliability product. So, Rick, can we optimize points like in that? I know we've talked in our last webinar or our last podcast about voltage and parameters and all that. We know that in the 3A type arena, we need to use higher voltage and higher isolation and lower continuity. But what can we get away as far as with test points?
So Todd, if we want a board to be ultimately 1,000,000% reliable, then no, we can't optimize any test points out of it. We need to test everything that's open and mask. And this includes not taking some enhancements, speed enhancements on some machines. Some different manufacturers have different types of speeding up the test process, but we should be applying a voltage and current to everything open and mask and measuring to make sure that it meets the other end of the net, the midpoint of the net, that all connection points are there. Now, Todd,
sorry, we bumped into each other once. When they do this, when we're talking about a Class C product, and sometimes they do allow perhaps, resistance only test on the probers, which is usually doubtful. But when you have to do this scenario, when you're talking about having to test all test points, time being one factor, but what kind of cost associated with this? Like if you had to do a flying probe test with all the test points or a fixture with all the test points for the customer pain level, I mean, what are the big cost differences here?
So there's a cost to every test point. To make it really simple, there's a cost to every test point. So if you have one test point, there's a small cost, and if you have 100,000 test points, there's a huge cost associated with that. But sometimes, if you're talking flying probe, the cost may be in test time. Your test time will increase. So even if you have a job with 3,000 test points, for example, and you're testing on the flying probe, it may take a few seconds to test this board on the flying probe. And on a fixture, it could take similarly 2 or 3 seconds, whereas a flying probe, 30 seconds, a minute, something. But as you go up in test points, let's say you have a board now with 25,000 test points. Now that board takes a few minutes on the flying probe, but takes a few seconds on the fixture tester, a grid tester, universal tester, dedicated tester, something that uses electrical test fixture, could take 10 to 20 seconds. So it's taking more time, but that 25,000 point fixture also takes a lot of time to engineer, build, and construct. This is why most people are not using electrical test fixture for small volumes, because it's not cost efficient unless it is required by the specifications. And we've seen jobs, Todd, we've tested boards before, 130,000 test points. 130,000 test points, you're looking at a minute on a fixture, and you're looking at several minutes, maybe over an hour on a flying probe machine. It all depends on the layout of the board itself.
I know we talk about specifications, and we follow that 9252 here like the gospel pretty much, because it's what the industry accepts. But I know that there's a lot of companies now, with everything cost and labor in the U.S. or North America, that they've outsourced a lot of manufacturing for commercial product. And what assurances, or do the other countries that do manufacturing, do they follow the IPC standards for 6012 and 9252 outside outside the U.S. and Canada?
Todd, let me give you an example of what happened in Gardien. In my position in Gardien, I had to responsible for quality. So one of the things that I did in the beginning was I implemented a certificate of compliance with some sort of standard. And in doing this, I found out that some of the CAM process or tooling processes, especially related to test point optimization, varied from country to country. So one of the first things that we did is we started a training program. I started a training program about the different levels, and I used the IPC 9252A document at that time to do the training. But other countries, I found in Europe and North America, yeah, they understood the different IPC classes, 6012, 5056, 5884. They understood all that. But when you went to some other countries, no, they didn't care. They didn't care. They didn't follow it. They were just doing mostly some type of optimization. So as the specifications matured and we moved IPC 9252B, generated 9252B, we taught our team in other countries to assign according to the specifications. And to this day, we still have the specifications listed on our CFC of compliance. So when you're looking for a printed circuit board and you're going overseas for it, just double check that they actually are understanding the documentation and specifications associated with what you have put in your fabrication drawings. That was a very good question, Todd.
So you think for people that are actually sending their commercial work off, it would be good to make sure that in their procurement document they state straightforward what they want, what specification, and it might be more of a insurance policy to make sure they audit, to make sure they're doing that type of thing. Otherwise, you don't know what you're getting when it comes back. I mean, it's got a stamp on it, but how robust is that stamp really?
It's like material, Todd, FR4. How many different flavors of FR4 are there? Now, if you just put in your specification FR4, they're going to use probably, depending on what fabricator's doing, they're going to use a low end to a medium end type of material. So specify what you want. I know a lot of people now are putting in the actual company that they want to, whether it's DuPont material, Rogers material, etc. They're putting that right into the specifications, and during the quoting process of the PCB, that is clearly specified that's what they want. So if you're going down to that level on the material itself, Todd, we should be doing the same sort of thing with reliability. What kind of reliability test do we have? I know that in Gardien, we have a whole bunch of different kinds of reliability tests, not only related to electrical tests that I'm sure we'll get into in the future podcast, but there's many different products out there. We do high pot, we do insulation resistance, micro short, various different tests like that, all to make sure that you have a reliable PCB board.
Great, Rick. That was very informative as well, to make sure that you're stating what you want and making sure what you're getting is what you specified. Well, that kind of wraps it up today for us today, talking about IPC, test point generation, assignment, classes, and so forth. We thank you for being with us today. Do you have any final comments, Rick?
Thank everybody for listening and watching. And I know that we mentioned a lot of graphics in this. So if you want to check out, and you're listening on a podcast, you want to check out the video for this, please see the links in the podcast below to go to our YouTube channel to look at the video associated with this. Thank you very much for listening.
All right, folks, wherever you may be, thank you for joining us. If you want to drop us a line, send us to info@gardien.com. That's info@gardien.com. Look forward to seeing you on the next podcast. Have a great day.